Yeah. So are you ready to start the talk?
Yeah.
Okay, then maybe we can slowly start. So yeah, welcome everyone. Today we're very happy to have Hannah Dell from the University of Bonn, and she's going to be talking about categorical Torelli for cyclic covers. So please go ahead.
Thanks, Pedro, for the introduction, and thanks a lot for the invitation to the seminar. Yeah, really excited at the opportunity. And yeah, please stop me anytime, especially because this is a Zoom talk. Like I'll try to stop and make space to ask questions, but yeah, please interrupt. Okay, so yeah, I'm talking about categorical Torelli theorems for cyclic covers. And this is a joint work with Augustinus Jaclowskis. Who is at the University of Luxembourg. And Franco Rota, who's just moved from Glasgow to the University of Paris-Saclay. Okay, but I want to start with a general question that I'm interested in, which is how do geometric invariants behave under finite group actions, or just group actions? So this is a question I thought about a lot in my thesis in the context, well, where these invariants were coming from Bridgeland stability. But today I want to talk about, yeah, this project that we put on arXiv a year or so ago, where the invariants are going to be some kind of categories called Kuznetsov components. So in the first part of the talk, I'm going to introduce those categories, motivate these categorical Torelli theorems, and in the second part of the talk, we're going to look at cyclic covers, so that's where the group actions are going to come in. Okay, so let's do categorical Torelli problems. And by the way, there's a nice survey with way more details by Laura Patuzzi and Paolo Stellari, which I'd recommend to check out if this piques your interest. So we're going to take x and x prime, two smooth projective varieties over C. But actually, this is mostly going to be true for characteristic 0 or large enough. Okay. So here's a theorem of Pierre Gabriel from the 60s, which says that if we have an equivalence between the category of coherent sheaves on X and coherent sheaves on X prime, so this is as C linear categories, then we get an isomorphism of X and X prime as complex varieties. So this category of coherent sheaves is really an invariant, a geometric one. It knows about the geometry. Okay. Here's another theorem of von Dahl and Orlov from quite a lot later, 2001. So firstly, we're going to ask that kx, the canonical divisor, or minus kx, is ample. So if we have this assumption, and we have an equivalence between the derived category of coherent sheaves on X and the derived category of coherent sheaves on X prime, then we still get an isomorphism between X and X prime. Okay. So this invariant, right, it's huge. I want you to, for today, just think of objects here as complexes of coherent sheaves. So it's an algebraic gadget that knows about, yeah, all the homological algebra of your coherent sheaves. So despite this, what this theorem says is it still knows about, yeah, it knows about geometry despite being kind of this big and complicated object. There's some way to recover to recover your geometry in there. Okay. And yeah, the other thing I want to just say next is that, this assumption about the canonical divisor, it is important. For example, if we take an abelian variety, then the derived category of the abelian variety is always equivalent to the derived category of its dual abelian variety. But there are abelian varieties such that are not isomorphic to their dual. So this can fail in this case, and it also fails for, or can fail for K3 surfaces. So there are kind of two directions you could then go to build on this result. One is, yeah, look at the case where Kx is trivial and find kind of another, if you have an equivalence, find something else about your variety that is still preserved. And there are many works in this kind of direction. But what I want to talk about today, this categorical Torelli story, is about asking, okay, if we keep these, so especially if we look at Fano varieties, then this huge invariant knew about the geometry. So do we actually need less information? Can we throw some stuff away and still recover our variety? And that's what we're going to do. That's what these Kuznetsov components are going to be that I mentioned already. So before I can define them, we need the following definition. So D is going to be just a triangulated category now. But you can just keep dbx in mind. So semi-orthogonal decomposition, or SOD for short, is a collection, which I'm going to write like this. So D is equal to A1 up to AN. So such that each AI is a full triangulated subcategory. So full just means that the inclusion of your category as a subcategory is full or surjective on homomorphisms. Okay. Now the next part is the semi-orthogonal part. So this says that the homs from AI to AJ vanish whenever I is greater than J. So there are no morphisms from right to left in this list as I've written it, but it could still happen that there are morphisms in the other direction. That's why it's only semi-orthogonal rather than orthogonal. Okay, and here's the third part, which is that the decomposition part. So for any object in our category, there's a sequence of morphisms and objects from En down to E1, E0, such that the cone of each EI to EI minus 1 is in AI. Okay, so this cone construction is something like a generalization of co-kernel to a triangulated category, but what I want you to really take from this part is that it means every object can be built from objects in each of these AIs by taking extensions, roughly. And actually, this decomposition is unique. Okay. Any questions? on that. Okay, let's see some examples, yeah? So oops. So here's a fact, which is that Fano varieties in general have non-trivial semi-orthogonal decompositions. So they're going to be useful for the setting. And yeah, for example, let's take X to be Pn, then dBx that has a semi-orthogonal decomposition like this. So we take OX and then we twist up to OXN, so twisting by some choice of ample. And yeah, just a warning here, I'm abusing notation. When I write OX, I really mean the full triangulated subcategory generated by OX. Okay, but here, hopefully, you can see that indeed there are no morphisms, there are no homes from right to left. So that's the semi-orthogonal part, but the decomposition part is a bit more subtle. That needs a bit more work. That uses this, it's called the Beilinson exceptional collection. But yeah, this Beilinson sequence. Okay. Now, another example. Let's take X, a cubic threefold. Then dBx has this semi-orthogonal decomposition. So I'll tell you what this AX is in a moment. So again, we have OX and OX twisted by 1. So what is this other piece? Well, these are just the objects that have no homes from OX and OX1. And this is what we call the Kuznetsov component of a cubic threefold. Okay. Now, why have I told you about this category? Well, here's the crucial theorem due to Banadara, Macri, Merotra, and Stellari, which says that if we take X and X prime to cubic threefolds, and there's an equivalence between these Kuznetsov components of AX and AX prime, then we get an isomorphism still. Okay, and this is showing that we can indeed throw away information from this Bondar-Orlov result and still recover the geometry. But yeah, probably this kind of category, just looking at the definition, it's not clear why this should know anything about geometry at all. So maybe, yeah, I mean, this theorem is telling you that it does, and maybe I'll just give you a quick idea of the proof. So firstly, we want to consider, and this is just as a black box, the moduli space of Bridgeland stable objects in AX of class numerical class ideal sheaf of a line, so the same Chang characters as the ideal sheaf of a line. So something to check, maybe as an exercise, is that this ideal sheaf of a line actually, yeah, it lives inside this category. It has this Hom vanishing. So what's this moduli space? I want to call it M sigma AX IL. So I don't want to get into what the stability condition here is, but if we black box this, what I want you to know is that, yeah, what they show is that this is isomorphic to the Fano variety of lines on X. So that's already something pretty geometric. So how are we going to use this with our equivalence? Well, what they show is if you have an equivalence between AX and AX prime, then you get an isomorphism of these moduli spaces. Say X, L, X prime, I, L prime. And this is really a non-trivial step. I mean, if you take a stable object in a category and apply an equivalence, in general, it's not clear at all whether it's still going to be stable. And yeah, also with respect to the same stability condition. But yeah, here it is. So then, of course, we get an isomorphism between fx and fx prime. So yeah, here they're really using that actually this category, it doesn't have so many stability conditions. So yeah, the fact that we can do this step is really something special about the category. Okay, so, and then yeah, finally, if you look at the Albanese variety of the Fano variety of lines, this is isomorphic to the intermediate Jacobian of the Fano threefold. So we get an isomorphism of the intermediate Jacobians, and then we can just conclude with a classical Torelli theorem for cubic threefolds, which says that they're determined by their intermediate Jacobian. And that's a result of Clemens and Griffiths and Turin. Okay. Questions about that?
Could you repeat what you said about the stability condition? So if you have equivalence, don't you can you not pull back a stability condition or something like this? I don't know how that works.
Yeah, there are definitely ways to pull back stability conditions, but yeah, yeah, right. I'm a bit vague. What am I trying to say? Yeah, I guess the difficult thing is to show if you have an equivalence and a stable object. When you pass through the equivalence, it's still stable. But also, yeah, firstly that it's still stable. So that's something about the stability conditions itself. Like if you have a big stability manifold and you apply an equivalence, probably you're not going to be stable anymore. But then the other aspect is if you apply the equivalence to your object, well, here they show that you actually still get an ideal sheaf of a line. Like you could get something else and then you would have kind of some other moduli space instead on the other side. Yeah.
I see, thanks. So if you have the stability condition pulled back from the other category, then even if you take the image of a stable object, it's not necessarily stable. That's what you're saying, right?
Right. If you take the pullback stability condition, I think it would work because I think that's how this pullback thing is defined. Yeah. Hmm.
Okay, maybe we can discuss in the end.
Yeah. Yeah.
Thanks.
Yeah, thanks for the question. It's a good point. Okay. Other questions? Okay. So yeah, this is the story for cubic threefolds. And hopefully you're wondering now, does this happen for other varieties? So here's the categorical Torelli problem. So if we take X and X prime, varieties of the same deformation type, with Kuznetsov components. I haven't told you how to define them, but bear with me. That are equivalent, so AX and AX prime again, AX prime, then do we still get an isomorphism? Okay, and yeah, so this definition of Kuznetsov component is pretty ad hoc for kind of each, say, deformation type of a Fano variety. So in a way, it seems quite unnatural that, yeah, you kind of come up with this category and then somehow it's the right one. It knows about the geometry. That's kind of what this problem is saying. But yeah, I want to convince you that yeah, that this really works in many cases at least. So for example, so firstly, I want to kind of make this a bit clearer for Fano threefolds. Oh, I lost it. Okay, one sec. I have to go steal this. So I've put together this huge slide with a lot of information, and I don't, you know, I just want to give you a feeling of what's going on. I'm not going to go through all the details, but so cubic threefold, it's a prime or Picard rank 1 Fano threefold. So it's sitting here, actually in this. So here, what I'm showing is this a classification of Picard rank 1 Fano threefolds. So for most of these, we know the answer to the categorical Torelli question. So for index 2 Fano threefolds, so basically ones, yeah, which includes the cubic threefold. The Kuznetsov component is defined in the same way as you look at O and O1, and then you take what's orthogonal to it. Sometimes you get like the derived category of a curve being equivalent to this Kuznetsov component. In other cases, you get some vector bundles, and in other cases, it's not so clear. There's such a concrete geometric way to describe the category. But still, in these cases from degree 2 to 5, this categorical Torelli theorem does hold. And the way it's proved is in a very similar vein to what we saw up here. So you show that stability is preserved, and then you find kind of a geometric moduli space. It's not always the Fano variety of lines. Sometimes it's like the Hilbert scheme of conics, this kind of thing. Okay. And then this bigger table here, we can see that the behavior is a bit different. So, okay, firstly, some cases, the Kuznetsov component is just what's orthogonal to O. But in these higher genus ones, it's O and some kind of canonical vector bundle. That's what these E's are. But so what's the answer here? So for many of these, categorical Torelli fails. They're not necessarily isomorphic, but they are, you do get a birational map between X and X prime. And people have, yeah, so a lot of work's been done here over the last decade to investigate all of this. But when you do have this birational Torelli, then yeah, people have shown that you can ask for, if you have an equivalence plus an extra bit of information that's preserved, then you can still get an isomorphism. So then, okay, it's like going from Bondel-Orlov, we threw away too much, but if we add in a bit more, then we can still get back geometry. Okay, so as you can see, the answers, this question is mostly settled for these prime finite threefolds, but there are these kind of 4 cases where we don't know the answer. And yeah, these 2 at the bottom in orange are what we looked at in this project. And these are going to actually arise as cyclic covers, and that's kind of our idea, was to really use the geometry there of the extra geometry and structure from the group action to say something that we couldn't say with the usual methods. Yes, because this kind of, I wanted to show you this moduli space approach, so I could also tell you that this doesn't work for these remaining cases. And one of the big problems there is that this category is bigger, for example, in terms of homological dimension. So there are a lot more stability conditions. So it's not clear whether stability is preserved and you can match up these moduli spaces like you could before. Okay. Questions? That was probably a lot.
So what are actually the refined CTT?
So basically you just ask that, I think they ask that, so you have this equivalence from AX to AX prime, and I think they ask that the projection of a skyscraper sheaf is sent to the projection of a skyscraper sheaf by this equivalence, or yeah, something roughly like that, because so basically the skyscraper sheaf does not, I think, in general live in this category, but you can project, which is some functor where you basically kill some homomorphisms until you get something that does live in your category. So they check that this object or something similar is preserved by the equivalence, and then they can look at the moduli spaces of stable objects with this class and know that they're preserved, and use that and study the geometry there to try to recover, to get an isomorphism. Yeah.
Thanks.
Thanks for the question. Other questions?
So in the cases where it's not possible to recover, is it maybe possible to recover just from the complement of the structure sheaf, or also not possible?
Like including this vector bundle, right?
Yeah.
Yeah, I don't know actually. Yeah, maybe you should expect that it would work, like, but it's something in between again. Yeah, I'm not sure.
Thanks.
Let's keep going. How am I doing for time? Okay. Then yeah, I want to also mention kind of another. Oh, yeah, let's also come back to this perspective. So I also want to mention another kind of a family of examples that's been studied that are not necessarily finite varieties, but where this question is still interesting. So Huybrechts and Renamo, and also Roscoff, studied the case where X and X prime are hypersurfaces in some projective space. And they showed that so if you have, right, X and X prime are isomorphic if there's an equivalence between the Kuznetsov components. So this is similarly defined as orthogonal to some line bundles. But they need an extra assumption as well, which is that this commutes with a natural autoequivalence. which I'm calling R. So you tensor with OX1 and then do this projection that I mentioned, where you kind of kill some HOMs to make sure you land in this Kuznetsov components. And this assumption is necessary in some cases. For example, if you take a cubic fourfold, then yeah, dbx looks like ax, ox, ox1, ox2. And yeah, for this category here is not enough. It's not enough to just have an equivalence. They need this extra assumption. And what they do is to relate the Hochschild homology of this category back to the Jacobian ring and play a similar game like with the intermediate Jacobian from before. But for them, yeah, the cohomology of this category is really a key ingredient and is going to be similar for us for our kind of examples. Okay. So I think now, yeah, I want to state the main result. So I'll just say, yeah, I'll just write down what I said already, which is that, so this X2 and Y1 Fano varieties in this table in the first example arise as branched cyclic covers. And we want to exploit this extra group structure to recover the varieties with kind of different techniques that don't use this moduli space approach. So I'm going to let curly X2 and curly Y1 denote their moduli. Then here's the main theorem with Augustinus and Franco, which says firstly, here we go, that if X, I'll put it here, X and X prime are of this X2 type, and X is very general, and this equivalence between AX and AX prime is Fourier-Mackay type. So this is an extra assumption that we need to make sure some extra structure on the category is preserved, basically, which, yeah, we should see at the end. So then we get our categorical Torelli theorem. We get our isomorphism of X and X prime. Okay, and here's the second part. So if we take X and X prime instead in this Y1 category and make the same assumptions, so X very general and phi of Fourier-Mackay type. But then we also need an extra assumption, which is that phi commutes with this rotation functor. And yeah, once you have this, then you indeed still get your isomorphism of X and X prime. Okay, and now, yeah, just a remark before I finish this part of the talk.
Sorry, Hannah.
Yeah.
What's Y in the theorem? Y?
Sorry, what's Y? The Y1.
X2 and Y1, yeah. So,
yeah, I'm using these curly notations to denote the moduli spaces of X2 Fano threefolds and Y1 Fano threefolds. So one way you could define, say, the X2 one is you look at all Fano threefolds of index 1, genus 2. That's this bottom row in the table. That's what this X2 space is. But I'll also tell you a more geometric way to interpret these as well. And y1 is then, yeah, this bottom row, so index 2, degree 1.
I
Yeah,
see. Thanks.
does that make sense? Okay.
And maybe could you write a little bit larger?
Yeah, okay,
Yeah.
sure.
Thank you.
Yes. Yeah, that's the problem with this two screen approach. Okay. I can I mean I can also just switch to one screen if that would be better. Yeah, maybe we can do that for now, and then I might bring if I want to show you more things from earlier, then I'll bring it back. Okay. So yeah, some remarks about this result. So firstly, this first part was proven by different methods in work of Xin Lin and Shiju Zhang in a result that came out the same time as ours. And then the second part was also proven, but without this R assumption. In work of, put it here, Lin Shenlin, Jürgen Renema, and Shiju Zhang last year. And yeah, what they do here is they consider x2 and y1 as hypersurfaces in projective or weighted projective space. And yeah, maybe what I wrote here is a bit vague because there are actually some assumptions on the hypersurfaces. So not all hypersurfaces are covered. Some assumptions on the degree of the hypersurfaces. Okay. So what they do here is kind of extend the ideas of the hypersurface case to these examples, and they also use some kind of matrix factorization categories, and yeah, it's a very different approach. Whereas yeah, we instead use this kind of group action perspective. But yeah, it's interesting that yeah, they can remove this assumption because yeah, hopefully you'll see at the end why we needed it. Okay, but I guess it also means there should be a way to remove it from our case too, which is something we're trying to think about. Okay, so now I want to move on to the second part of the talk where I discuss branch cyclic covers. But yeah, I just want to check if there are any other questions first. Okay, so yeah, for the rest of the talk, I really want to explain the ideas behind the proof, behind our approach. So here's the general setup. Okay, yeah. So X is going to be, okay, so really we start with Y, an algebraic variety, or proper Deli-Mumford stack also works. And then we pick a divisor here. So I'll say it like this. So, and then once you pick a divisor, yeah, let's say an O, Y, and D, you can cook up an n to 1 cyclic cover. So that's what X is. X is our degree and cyclic cover of Y ramified over Z. I'll just give these maps some names. So Fi, then we also have a map here, J. And then there's the covering action. There's the cyclic group of order n acts on X. That's coming with this cyclic cover. Okay. Yeah, now I do want to bring this back, and then so maybe I do just need to start writing bigger. Because I want to give where should I put this actually? I think I want to put it here. Let's put it here for now. So I want to take as a running example. Please just tell me if I need to write bigger again. X2. So X2, it arises as a 2-to-1 cover of P3 ramified in a sextic. P3, 6. Okay. So this is F and J. So we have the cyclic group of order 2 acting on the top. And Y1 is similar, but you instead have weighted projector space here, P1112, and a sextic here again. Okay. So maybe I'll just leave this. Yeah, let's do it like this. Now I want to make some assumptions before we can say something about the derived categories. So assume I just realized maybe it was less clear because on one side the pen was thicker than the other. Okay. So let's assume firstly that Y has a rectangular Lefschetz decomposition. So this just means the following. So we can pick an ample divisor and let's use that to twist the structure sheaf. And admissible subcategories B and dBy such that dBy has a semi-orthogonal decomposition, which looks like firstly you take B and then B twisted by 1 and so on up to B twisted by m minus 1. And yeah, examples of this are weighted projective spaces. So yeah, hopefully this reminds you of the semi-orthogonal decomposition we saw of projective space earlier. So this was with O up to On. But yeah, so this works more generally for weighted projective spaces, for Grassmannians, and other homogeneous spaces. So for our example here, we have dBy. Well, Y is just projective space, P3. So we have O, O1, O2, O3. Is this big enough now?
Yeah, I think it's good. Yeah, thank you.
Okay. Now, one more assumption, which is a numeric one, which is that capital M, which is m minus 1 times D, is greater than 0. So what in our example over here, right, we have n is 2, D is 3, little m is 4. So our big M, no, I messed something up. yeah, we're fine. We're doing 4 minus 3 and it's 1, which is greater than 0. Great. So we're in good shape there. Right. Now here's the theorem of Kuznetsov and Perry. About which tells us when we have these assumptions, the derived category of X has a semi-orthogonal decomposition, which looks like, so this Kuznetsov component, which is defined as the orthogonal to basically pulling back each of these twists of this category B from up to big M minus 1 times. So that's why we have this assumption about M. Okay, so what this is saying is we can take these categories on the base, pull them back. We still have this semi-orthogonality, but there's something left over, and that's exactly how you define the Kuznetsov component as all the objects with no HOMs from each of these in these cases. So you can just take that as the definition for the rest of the talk. Okay, so how does this look in our example? Well, a bit boring. So we just have AX and then OX. And this was what we saw up here already for this X2 example here. Okay. So that's what DBX looks like. But ultimately we wanted to use this. What we wanted to do was get a categorical Torelli theorem. So start with an equivalence of these Kuznetsov components and get an isomorphism of X and X prime. So how are we going to do that is the idea or a question. So suppose we have another branched cyclic cover X prime with the same base, but a potentially different divisor, but in the same linear system into 1. So if we have an equivalence AX prime, then what if we could find a way to show that the branch divisors Z and Z prime are isomorphic? Then maybe we could use that to reconstruct our variety and get our categorical Torelli theorem. So that's going to be our strategy. But how is this going to work? How are we going to get this information about Z? Well, the key observation is that DBX doesn't see Z, but once we remember this cyclic group action and look at the derived category of the quotient stack, which is the same thing, equivalent to the equivariant category of X. I'll tell you more about that in a moment. So this category it does. Okay, right now this is super vague, but yeah, this is where the group action is going to come in to help us get information about the branch divisor. Okay, so now to explain what I mean by this, we're going to take an equivariant interlude. So if we take G a finite group and D C linear category, but you can just keep our setting in mind. Yeah, here we could put just coherent sheaves. We wouldn't you don't need the derived category of coherent sheaves for this definition. We don't need this triangulated part, that's what I'm trying to say. Okay, so a group action, or yeah, I'll just call this a group action, but it's also sometimes called a strict group action in the literature of G on D is given by, firstly, autoequivalences. VG from D to D for every group action. But it's more than this. So we also ask for, as part of the data, that there are isomorphisms epsilon GH from VG compares with VH to VHG for any two group elements. And then the third part is like roughly associativity. So these, this 2 and 3 makes this more than just saying a group action is a subgroup of the group of autoequivalences on your category, because yeah, it's really asking for extra structure here, because we're asking, okay, so in general, if you take a subgroup of the group of autoequivalences, you'll have a natural isomorphism when you compose like this, but it's not necessarily the same on every object. So this is asking that it is the same on every object. Okay. Oh, yeah. But this is just some extra structure that we need to make sense of the equivariant category. So now I'm going to write G acting on D for such a group action. Then we can form what's called the G equivariant category of D, or G equivariantization. And yeah, this generalizes the notion of G equivariant sheaves. So the objects of this category are pairs E and lambda G. Such that each lambda G is an isomorphism between E and phi G applied to E. So in particular, it means the first that E is invariant under this group action, but this category is more than the invariant objects, because you also remember your isomorphisms, you remember how you're invariant. Okay, plus there's also some compatibility here about when you compose them. And then, yeah, morphisms in this category are just morphisms in the G equivariant category that commute with these lambda Gs. Okay, but that's all I wanted to say, kind of abstractly, about these equivariant categories. Now I want to get back to what this means in our setting. But yeah, maybe I'll just check if there's any questions first.
Yeah, actually, I don't really understand the difference between an autoequivalence and an isomorphism.
I guess like let's see. What's a nice way to explain this? So yeah, the isomorphisms are really as functors, but the autoequivalence, so that should be a functor that is fully faithful and essentially surjective. So you get like your Hom spaces are isomorphic when you apply the functor, and is it? Sorry, yeah. Now I'm blanking on the definition of autoequivalence, but it's not necessarily. Like it's not really like a bijection of sets anymore. That's kind of
Okay, yeah. Thank you.
how I think about it. But yeah, I'm not.
It's just like I don't really
Yeah.
understand derived categories, but yeah.
Written.
Okay. Okay. Yeah, and maybe you need to start writing a little bit larger again.
Again,
Yeah,
okay,
thank you.
thanks. Maybe, don't know if I can. Cool. Other questions? Okay, let's keep going. So now, yeah, so like this. So let's get back to the cyclic covers. So for us, we have the cyclic group of order n acting on dbx by, so this action is given by pullback. So so on the category of coherent sheaves, we can pull back along the morphism from the group action, and this lifts to the derived category. And this is in fact a strict action. You get these natural isomorphisms from the fact that, yeah, from this. So this is kind of the extra structure that we're looking for that you don't have with any autoequivalence. Okay, so because we have this, we can take the mu n equivariant category, which, yeah, I also might call that equivariant Kuznetsov component. Yeah, there's a bit more to say about this. So so up here, okay, so we have an action here on dbx. Like we can only take the equivariant category if this action restricts here. Like in other words, we want to make sure that if you have an object in here and you apply the action, then you stay inside the Kuznetsov component. But this actually happens because for us, these categories here are all pulled back from the base. So they're basically invariant under this mu n action. So these are all preserved, which means also AX is preserved. Okay, so, okay. All that's to say is we can take this equivariant category and now, actually for the rest of the talk, I want to really focus on this X2 example. So maybe I'll just copy, where did it go? Maybe I'll just copy this and then we can just sort of continue. Okay. So what I want to tell you is that, yeah. So firstly, we can take the equivariant category of dbx, and this has a semi-orthogonal decomposition where you take the equivariant category of each piece. And this is something that only works if you know that this action restricts, basically. Now, It turns out there's another SOD for this category, which comes from being a branched cover. So it looks like pulling back firstly the base, and then pushing forward this this branch divisor along this morphism here, J. Yeah, I'm abusing notation a bit here because, yeah, this is the equivariant category, so the objects aren't just, say, like here, it's sheaves, it's objects pushed forward from DBZ together with these isomorphisms where you remember how you're invariant. Okay, so there's also some equivariant structure here. But what you do whenever you have two different semi-orthogonal decompositions is you try to move them or move the pieces around and match them up. And using that, we can describe this equivariant Kuznetsov component a bit more. So we have AX mu2, looks like the push forward of DBZ, and then two exceptional objects. So by this, I mean that the Homs, the Hom spaces, they only have like one dimension of Homs in degree 0. Okay, so this category, it almost looks like DBZ. Well, it has Z in there, and that's what I meant when I said this thing about how the equivariant category can see Z. So this DBZ, it shows up as a semi-orthogonal component here. Now, yeah, what we, yeah, maybe I'll just pause for questions actually before I say more. Okay. So what were we trying to do again? So I had this question too, this hope of going from the equivalence to an isomorphism of Z and Z prime. And what we originally hoped is that, yeah, we could just get, take this category and get an equivalence between DBZ and DBZ prime. But that doesn't work because you have these other exceptional objects swimming around here. Like you don't know if you have an equivalence. It might be that, yeah, things get switched around. Semi-orthogonal decompositions are not kind of canonical in this sense. They're not preserved by equivalences. So what are we going to do instead? Well, yeah, before I get into that, I want to make a few remarks, actually, just about this theorem. So yeah, just firstly, this generalizes to branched cyclic covers with this numerical assumption that this big M is between 0 and D. So what you get there instead is this AX mu N is going to be N minus 1 copies of something like what's written here. So you have DBZ showing up and then some exceptional objects and then repeated, but with some different equivariant structure, basically. Okay. And also this extends and was really inspired by work of Kuznetsov and Perry to Z canonically polarized. So for them, they look at the range they look at the range M equal to D and greater than D, which corresponds to, yeah, for example, when M is greater than D, that means the branch divisor is Fano, and they get kind of different behavior. But so yeah, our results cover this new case. So we get, yeah, descriptions of this equivariant Kuznetsov component for more examples of branch cyclic covers. And one more thing, which is that Orlov and Hirano and Uchi have analogous results to this theorem for matrix factorization. So in the language of matrix factorizations. Yeah, which is pretty interesting to us. Yeah, something else we're trying to think about is how these perspectives are related. Okay. So if I lost you, all we need for the rest of the talk is that we want to answer this question too. So I think I'll just copy it so we can stay zoomed in. So what we're going to do for the rest of the talk is try to extract this Z. So firstly, by passing to the equivariant category. And then secondly, by passing, by extracting, getting the information about Z from here, and that's really going to use this semi-orthogonal decomposition. That's why we did this. Okay. Yeah, and I think.
Can I ask about this canonically polarized? Isn't C hypersurface degree 6 always canonically like canonical Lyman ample? Or does it mean something different?
Yeah, that is what I mean. But what I mean is, yeah. So, okay. So as I've written, the way I've written the theorem, it's just for this example of X2, right? So when I say to canonically polarized, I mean this kind of generalized, this more general version of the theorem that works for other branch cyclic covers. So that's allowing for, yeah, different bases, different
okay. So
ramifications.
as long as it is
we're in
canonically
this,
polarized. I see.
So as long as we're in this range, that's basically what it means for Z.
I see. Thanks.
But I think, yeah, there are still some, basically, if this gets too canonically polarized, then we can't cover it with our results. That goes outside of this M range. That's kind of what this big M is controlling. Yeah. Other questions? Okay. Then I think I want to spend, yeah, like 10 minutes, the last 10 minutes or so explaining this step B, because that was really the hardest part for us. Kind of how do we get the information of Z out, because we have these other exceptional objects that are sort of in the way. Okay, and here's the key to B. Which, yeah, again, I'll just state in the X2 setting, but it does work a bit more generally. But here, for this theorem, we do need some stuff about being the covers being threefolds, for example. So this doesn't work so generally anymore. So if X and X prime are in this X2 family, of Fano threefold, so branch cyclic covers of P3, where the ramification was degree 6. Then if we have an equivalence of the equivariant Kuznetsov components, prime, which is Fourier-Mackay type, and if X is very general, then we get a Hodge isometry. Maybe I'll put this here. Between the H2 prim of Z and Z prime. So this H2 prim is the kernel of coupling with H when you go from H2 Z to H4. Okay. And how is this going to help us with the step B? Well, fortunately, there's a result of Donaghy from the 80s, which tells us that for these sextic surfaces, if you have this primitive, this Hodge isometry, oh yeah, I did want to say, also write that this is a Hodge isometry, because that's very important for this Donaghy theorem. If you have a Hodge isometry, then you get an isomorphism of Z and Z prime. And yeah, we have a similar, that this theorem also works for Y1, and then there's an analogous statement of Massa and Hiko and Saito, also from the 80s, that gives you this classical Torelli theorem. Okay, so this is how we do step B, but yeah, I'm really hiding the magic in theorems 3, so I just want to explain a bit more about that before finishing the talk. Yes, so here are the ingredients, at least. So I said we were going to try, quite a long time ago, I said we were going to try to use information about the cohomology of this category of this category of this Kuznetsov component to get geometric information. And what I mean more precisely is that we use topological K theory. So Blank, Jeremy Blank and Alex Perry show that the topological K theory, so, well, firstly, that there is a notion of topological K theory for categories, which works in this setting. And this, I'll say more about it in a second. But this is some, I like to think of this as like a big cohomology invariant. And this has a Hodge structure. And Euler pairing. Induced from the topological K theory of the stack X mod mu2. So really, this is the same as the topological K theory of the mu2 equivariant category, this dbx mu2 we saw already. So just to say a bit more about this, so if X is smooth, and we look at K top, just the 0 part over Q, then the Chern character gives an isomorphism to the even cohomology, rational singular cohomology of X up to some Tate twists. And okay, there are then these other kind of degree parts, which are kind of other twists of this basically. But all that's to say is, yeah, this topological K theory, I just want you to think of it as cohomology. But yeah, that's how it works for smooth. But okay, we're not actually in a smooth setting here because we're looking at X mod mu2. So what you actually end up having on the left is like cohomology of the inertia stack. Okay, but what this has already is a Hodge structure, and that induces one on the Kuznetsov component because it's a subcategory. Okay. And then, yeah, I just want to draw a big diagram. So we have K0 top of AX mu2 and K0 top of AX prime mu2. So the assumption that, I said we have this assumption about the equivalence being Fourier-Mackay type. mu2 Fourier-Mackay type. So precisely why we want this assumption is to make sure that there's a Hodge isometry between the two topological K theories of these equivariant Kuznetsov components. So this is, yeah, some extra structure that you put on a category. It's not necessarily clear if you have an equivalence that this structure is preserved. So this assumption is to make sure that it is. So once we have this, we can look at inside here K0 AX mu2. So that's just the algebraic K theory, or it's called also the Grothendieck group. So this lives inside the topological K theory. And I said we have an Euler pairing. So what we can do is look at the right orthogonal to that Euler pairing of the subcategory of this, of the sub K theory inside the bigger topological K theory. And why am I looking at this? Well, it turns out that this is the same as the orthogonal to K0 dBz. And this is really using our theorem 2. So this theorem 2 was about having a semi-orthogonal decomposition of the equivariant category that has dBz inside it. And this topological K theory, it sees semi-orthogonal decompositions. So this is theorem 2 plus that's a Riemann-Brock. So basically, using our semi-orthogonal decomposition, you can check what these, and looking at the Euler pairing, you can check what these orthogonality conditions mean. And actually, it's the same as the ones coming from, the same orthogonality conditions for dBz. And then finally, the Chern character gives an isomorphism between the K0 of dBz perp and the H2 prim. So that's why we're looking at this perp, because we can recover this primitive cohomology. And this part is using this assumption that X is very general because it ensures that that Z has Picard rank 1. Like potentially, otherwise this could be too small, I think. Okay, So then once we have this, we kind of pass our equivalence down and get Hodge isometries on the bottom. And in particular, that's how we get our Hodge isometry of the primitive cohomologies. Okay, so that's really the key to this this theorem 3. And then yeah, the last thing. Okay, 2 more things to say. So yeah, firstly, yeah, this assumption about the we had this assumption for y1 needing like the equivalence to commute with a rotation functor, and that is coming in for this first step to make sure that if you have an equivalence that it descends to the equivariant category basically, or lifts, is maybe the better word, which yeah is something you can get for free in the x2 case, but we didn't find a way to prove it in the y1 case. Okay, and the last thing I want to say is that yeah, I just want to come back to this question from the very beginning of how do geometric invariants behave under finite group actions. So for us, looking at the group actions gave us more information. It gave us a better invariant in that we could look at this equivariant Kuznetsov component, and that was more geometric in the end. That helped us recover the geometry. So I want to finish with a question for you folks, which is how does this question fit into your research? Do you have any answers for me? Okay, thanks.
Yeah, thank you very much for a nice talk. So is there any question from the audience?
Or answers?
So your question to the audience, the last question was question 1, or?
Yeah.
Yeah, I'm also interested in this question. Yeah, I think it's.
Is Y1 also a 2-to-1 couple?
Yes. Yes.
Oh, okay, okay.
Yeah, it's I can write it here.
Then actually, does the ingredients for theorem 3 does it work for any other covers of different degrees, or it only works for degree 2?
Good question. Yeah, so we really needed double covers here, actually. And why? So it's to do with so in general, this AX mu n category, it looks like you have kind of dBz, some exceptionals, dBz again, some exceptionals, and so on. But okay, each time you have different equivariant structure, really, like it doesn't really make sense to.
Oh wait,
to
so you don't
repeat.
have home from dBz to dBz? Or...
Well, yeah, so this is where I'm lying. So maybe I could instead write
okay.
it like this, dBz tensor rho. So we pick some representation of mu2. Sorry, I'll say, okay, let's say mu2 hat, like yeah. So you have an action on this equivariant category by tensoring with some representations, and that action is basically changing the equivariant structure that you have on an object. So the semi-orthogonal decomposition looks like taking each of these pieces, and each time you change the equivariant structure a bit. So yeah, that's why you have this kind of here, yeah. What am I trying to say? All that's to say is like we get several copies of this DBZ showing up. Okay, but with different equivariant structure. So kind of this part where we check the orthogonals, it's maybe not so clear what you get, or kind of we have specific kind of vanishing of this Euler pairing you can check for DBZ prep, and I think it's not so clear how to do it when we have several of these DBZs showing up. But yeah, I'm not entirely sure. It's a good question. It would be nice to apply this to higher degree covers. Yeah, maybe that's something we could talk a bit more about another time.
Okay, thanks.
So I want to ask about sometimes these phantom components. I think quite frequently they appear as, the construction involves some cover, some branch cover usually.
Yeah.
And yes, for example, in one case I remember it was Alexeev and Orlov, and yeah, they have an exceptional collection, and then this complement turns out to be such a almost phantom or something. Yeah, so would it? Do you think it can happen that you can do Torelli from the phantom component, that you can recover the varieties from the phantom component, which would be weird, but
Yeah, I think this is something that'd be really cool. My collaborator Augustine has some ideas for how to do this for some examples. I didn't know about these branched covers ones. But yeah, I think a warning here is that like the algebraic K-theory of these phantoms is usually 0. Maybe that's one way to define it. So yeah, it has to be, the techniques would definitely have to be something quite different to this sort of strategy. But that's also why the original stability moduli spaces technique doesn't work, because I think you can't necessarily put stability conditions on these phantom categories. That's definitely a problem.
right. Do you know if you mentioned this alternative proofs by Xun Lin and Xin-Chuo Zhang and company?
Yeah.
Do you know if they also use K-theory or they completely bypass this?
So they don't use K-theory, but they need this Fourier-Mackay assumption, because they also make use of some higher structure, which is coming from, they call it the Hochschild-Serre algebra, which is some algebra structure that comes from looking at the matrix factorization category. So I guess the first question would be, are these phantoms equivalent to some matrix factorization category? Then maybe you could do something, but I have no feeling for that.
I see. Thanks. Okay. Any more questions? Okay, then let's thank the speaker again. Thank you very much.
Thanks a lot for having me.